Hey everyone, so let's talk about one of the biggest headaches in AI right now. It's absolutely massive appetite for memory. Modern AI models, they're brilliant, no doubt, but they are also incredibly hungry. What if we could put them on a diet, though, without them losing any of their brain power? Well, we're going to break down a new technology called TurboQuant that pretty much does exactly that, pulling off what you could call near-perfect AI compression.
So how in the world does this work? Here's the game plan for today. First, we're going to tackle the core issue, the AI memory bottleneck. Then we'll look at the old ways of solving this and why they just don't cut it anymore. After that, we dive into the real magic of TurboQuant, this super clever random rotation trick and its two-stage solution. And finally, we'll look at the results, which are frankly stunning, and talk about what this means for the future of AI.
All right, first things first. Let's really get a grip on the problem that something like TurboQuant even needs to exist to solve. What is making modern AI so ridiculously hungry for memory?
Okay, imagine you're talking to this amazing translator. To follow a really long and complicated conversation, they need a notebook, right? They're jotting down key points, names, context, and the longer you talk, the bigger that notebook has to be. Well, large language models are basically that translator, and their notebook is getting so big it's becoming a real problem. And the main offender here is something called the KV cache. This is the AI's short-term memory. It's notebook. Every single piece of the conversation, every token, gets stored in there so the AI can keep track of the context. The problem is, for models trying to understand long documents or chats, this KV cache just balloons in size. It becomes a huge bottleneck that slows everything down and costs an absolute fortune in expensive hardware. Now, this isn't exactly a new problem. People have been trying to shrink this AI notebook for a while. So let's look at the classic approach, what I'm going to call the quantization compromise, and see exactly where it starts to break down. The basic idea for years has been something called vector quantization. It's just a fancy name for data compression. You can think of it like taking a huge, super high-res photo file and squishing it down into a much smaller JPEG. You're swapping out complex, really precise numbers for simpler, less precise ones to save a ton of space. And if you look at this chart, you can immediately see the issue with older methods like, say, product quantization or PQ. See that first row? Data dependence. Traditional PQ is offline. That means it has to study a big batch of data beforehand in this really slow, heavy pre-processing step. It has to learn the specific patterns in the data before it can compress anything. That just makes it way too sluggish for the real-time, instantaneous needs of a modern AI running on a powerful GPU. So how does TurboQuant get around all of this? Well, it all starts with a disarmingly simple but incredibly powerful trick that basically just throws that old, slow rulebook right out the window. The big idea behind TurboQuant is actually super elegant. Instead of trying to fight with this messy, complicated data where all the different dimensions are tangled up with each other, the algorithm's first move is to just simplify it. It takes the data vectors and just applies a random rotation to them in high-dimensional space. Think of it like taking a rough, jagged rock and putting it in a rock tumbler. The rotation smooths everything out. It makes all the different facets of the data, its coordinates, way more uniform and predictable. And as the paper itself says, this makes the coordinates nearly independent. And that is a very big deal. It means you can now look at and compress each piece of the data one by one, which is just so much faster and simpler. And that simple rotation trick is what unlocks TurboQuant's beautiful and super effective two-stage process for compression. This is really the secret sauce behind its incredible results. So it's a two-step dance. In stage one, the goal is just to get as close as you can to the original data. It compresses everything to minimize the overall mathematical difference, what engineers call the mean squared error, or MSE. So think of this step as making a really, really good, but not quite perfect, first sketch. Then stage two comes in. It's the cleanup crew, and its job is to fix the small but predictable errors, the bias, that first step introduced. Yeah, a warped mirror is the perfect way to think about why that second stage is so important. That first stage, the one minimizing the overall error, is awesome at getting the compressed version very close to the original. But it introduces this subtle, consistent bias. The reflection is almost perfect, but it's always distorted in the exact same little way. For an AI doing millions of calculations, those tiny, consistent errors can really add up and cause big problems. So stage two basically unwarps the mirror. It takes that tiny little bit of leftover error from the first stage, the residual, and applies a second really specialized one-bit quantizer to it.
This step, which is based on something called the quantized Johnson-Lindenstrass transform, is mathematically designed to perfectly cancel out that warp. It makes sure that any future calculations using the compressed data are statistically unbiased and super, super accurate.
Okay, so the theory is beautiful, right? A simple rotation, then this two-step dance of compression and correction. But does it actually work in the real world? Let's take a look at the results because they are pretty wild.
So check this out. This is a needle in a haystack test. The goal is simple. Find one specific fact buried inside a huge pile of text. On the left, you can see other compression methods, and they struggle. They miss the needle. But on the right, that's TurboQuant. Even when it's compressing the data by 4 times, its performance is identical to the original uncompressed model. It finds the needle every single time. That's perfect recall.
Now, in the world of information theory, there's a concept called the Shannon lower bound. It's basically the laws of physics for data compression. It is the absolute theoretical limit of how good you can possibly get. You can't do better. On this chart, that hard limit is the green dashed line. And the purple line, well, that's TurboQuant. It is practically hugging the theoretical limit of perfection.
In fact, the math proves it. The researchers showed that TurboQuant's performance is always within a tiny constant factor, about 2.7, of the absolute best case scenario. It is mathematically, provably, near optimal. So what does all that near perfect quality actually get us? Well, look at the savings. We can shrink the AI's memory, that all-important KV cache, down to just 20% of its original size. That's a 5x reduction in memory, with almost zero drop in performance. It's just incredible. Okay, let's bring this all home and talk about what this huge breakthrough really means, not just for AI nerds, but for every single one of us. So, to wrap it all up, TurboQuant isn't just some tiny incremental improvement. It's the whole package. It's lightweight, it works in real time, it's designed from the ground up for modern hardware, it's provably near optimal, and it gives us massive compression without hurting quality. And what that means for you and me is that the most powerful AI models out there can now run on way less expensive hardware. They can give us answers faster, and they can understand and process vastly larger amounts of information. Think a whole book in one go, without even breaking a sweat. It just makes truly powerful AI cheaper and more accessible for everybody.
And that kind of leaves us with one final, really exciting question. For a long, long time, memory has been this fundamental roadblock, limiting what AI could do. So, if we've just found a way to make that roadblock basically disappear, what amazing new things will AI be able to do next?